Fractionally Calabi-Yau lattices. Please.
Thank you very much for the invitation and the introduction. So, fractional Calabi-Yau lattices. The lattice part is the more combinatorial aspect of my talk, and my goal will be to transform the fractionally Calabi-Yau property, which is homological. It comes from homological algebra, into something manageable and combinatorial in the context of lattices. But first, I need to give you motivation on like why should you care about fractional Calabi-Yau lattices? And for me, a really good motivation is this paper by Frédéric Chapoton, with titled "Posets in Fractional Calabi-Yau Categories," in which he presents a surprising conjecture that starts with combinatorial sequences, which are on one side connected to the representation theory of n-dimensional algebras through posets that they count, and on the other sides are related to singularities because they're made up of Milnor numbers. And what Chapoton conjectures is that there should be a deep connection between these two blobs. By the way, can you see my pointer, or should I?
Yeah.
Yeah. Okay.
Yes.
Thank you. Thank you. And so. Yeah, I will give more details about each one of these blobs. I just want to say that the part that I'm more familiar with and that I will focus most of the talk on is the left blob, the representation theory of n-dimensional algebras, and specifically of posets. And what else? And I will try to draw your attention here to the fact that there is a question mark also on the left here. So, combinatorial sequences, what do I mean by that? So before, yes, so now I will describe the conjecture in more details. So before I talk about sequences, I will talk just about a single number. And that number will be S. It will be a positive integer. And I will say that S satisfies a product formula if you can write it as a product of a finite number of fractions where the sum of the numerator and the denominator of each of these fractions is a constant equal here to uppercase D. And so the data of the denominators and this uppercase D number, I will call this a weight. I mean, Chapoton calls this a weight. So first of all, let's make sure that these weights exist. They do. Any numbers, you can, like any number you want, you can write it as this number divided by 1. That is a product with one fraction in it, and the weight that you get is 1 semicolon S plus 1. This, I think we can all agree that we can call it a trivial product formula. But there are more interesting product formulas. For instance, if you take binomial coefficients, n choose n plus n, you can rewrite them as this product with n fractions. And you can see that the sum of the numerator and the denominator in each one of these fractions is n plus 1. And so the entire weight will be the integers ranging from 1 to m. Here are the denominators and this n plus 1. But of course, you can swap m and n. It's symmetric in this formula. So you get another product formula for the same number. So, okay, they exist, but they're clearly not unique, even in cases where they do seem to carry some information about the number that we're looking at. And the third example that I want to mention here will be Catalan numbers. So you can, the nth Catalan number is 1 over n plus 1 times n choose to n. And maybe you can show this, you could do this as an exercise, that it satisfies a product formula with weight made up of the integers ranging from 2 to n, and the sum of the numerator and the denominator for each of the fractions that will appear should be 2n plus 2. So that is the product formulas. We already see some sequences appearing, but let me now talk about singularities, which was the blob on the right and on the diagram of the second slide. And so I will now consider a polynomial function, and I will call it, and it is called quasi-homogeneous if it is close to being homogeneous. What do we mean by that? Is that if you apply the function f to entries where xi has been multiplied by lambda to the power of di, it's the same as applying f to the entries xi, x1 to xm, which is multiplied outside by lambda to the power of uppercase d. And in 1970, Milnor and Orlik showed that if f has an isolated singularity at 0, the Milnor number of the singularity is the product formula associated to the weight d1 to dm uppercase d. So to sum up what we've had so far, we have product formulas in geometry as Milnor numbers, and we've seen them appear through examples in combinatorics. And the examples we have in combinatorics, they come in families or sequences. And they are quite famous, and Catalan numbers are very famous. And if you look at, if you want to go and have a look at Chapoton's paper, you will see many more examples. And I think one can also say that these other examples are also famous. And something that maybe wasn't very clear so far is, so in the sequences in combinatorics, they count things, and usually in the example that I gave you, they count things that tend to be posets. And so we now want to have the language to connect these two sides beyond just saying that, oh, there are product formulas in both cases. So next slide, there will be a lot of notations about bounded direct categories. For this, we start off with K, a field, and we'll fix for a very big chunk of the talk a poset P, which is finite. We'll denote by A its incidence algebra. And it's important to note that it is a finite dimensional algebra, but also an algebra of finite global dimension. We will denote by D of A its vector space dual, and by D uppercase B of P or D uppercase B of A mod, the bounded derived category of finite dimensional modules over the incidence algebra, the poset. Here, I want to point out that its category is triangulated, and we will denote by 1 and a little bracket its suspension factor. And because the algebra is a finite global dimension, this category has a Serre functor, and the Serre functor here is the derived tensor product with the vector space dual VA. And these two bullet points are structures of the category. So being triangulated is a structure, having a Serre functor is another structure. And now comes a very important definition. What is fractional Calabi-Yau? Well, we say that a triangulated category with a Serre functor is Calabi-Yau of dimension d over L if the Serre functor applied L times is isomorphic as a functor to the shift functor applied d times, where d and L are integers. So what we're saying is that we are connecting the two structures that we have here for the category, these two types of symmetries, and we say that they're actually connected. And using this, we can give, I think, a satisfyingly precise conjecture for now. So I will state Chapoton's conjecture. We start with our sequences of non-negative integers, and we assume that for each n, the entry Sn of the sequence emits a product formula, and we will denote the weight as before, lowercase d1 to lowercase dm, semicolon, uppercase d. Note that I decided to not include n in this notation here on the right, but that's just to make it not too heavy. the weight depends on n. So the first part of the conjecture is that there should exist a family of posets, Pn, which are counted by the entries of the sequence. So their cardinals are given by the entries of the sequence, such that their bounded derived categories are Calabi-Yau of dimension C over D, where D is the one that appears here in the weight, and C is some data computed from the weight. In what way? By summing the difference of the numerator by the denominator of each fraction that appears in the product formula. So it's D minus Di minus D, and so D minus 2Di. And this is C. What we're saying here is that given a sequence, combinatorial sequence, we don't want any family of posets that are counted by the sequence. We want posets that actually encompass, see the product formula, but in order to see this product formula, or at least an image of it, you have to go into the bounded derived category and look at the fractional Calabi-Yau property. And the fractional Calabi-Yau dimension of this poset should record part of the weight. Okay, and so this is why there was a question mark in the little diagram on the second slide, because we don't know how to construct this sort of poset in a systematic way. Now, for the right part of the right blob of the diagram of the second slide, the conjecture says that there should exist a quasi-homogeneous singularity Fn with variable weights d1 to dm and total degree uppercase D, and a geometric triangulated category Fn, which would be Fukaya-Seidel, which is equivalent to the bounded derived category of Pn. So this corresponds to the arrow that connected the left part and the right part. Let me point out that what is the statement here is about the category Fn. Any quasi-homogeneous singularity with these weights would have the correct Milnor number, but we want more. We want this category. And so let me now give some remarks and also record some questions that I've been asked before when I was giving talks about this. First of all, why sequences? And the answer that Chapoton gives to this usually, and that I think I agree with, is that if you just have one single number that you can write as a product of fractions with a product formula, that is too much of a coincidence. There's no reason that you should be able to find a poset just with one number. That's not enough information. But once you have a family, you can hope to actually do this, or that this does have significance. But if it is a sequence that we start off with, how does the weight vary with n? And I have no answer for that. It is a conjecture, and so there is room for adding precisions to the statement. And in the same vein, let me point out that Fukaya-Seidel categories are complicated categories. I mean, I'm not an expert on them, but I think in general, there's not much known about them. And so maybe this is also a statement that should not be seen as completely precise. And so with all these remarks being made, why should you believe in this conjecture? So now I'm going to give you some examples, and I hope that you'll find them intriguing enough, maybe not to maybe believe in the conjecture, but at least think that there's something in there that can be of interest. So let's go back to the examples that were on the slide where I introduced products. And we'll start with the trivial weight. And so the sequence that we'll consider will be just a sequence of positive integers to which we associate the trivial weight. And so for each n, the sum of the numerator and denominator is n plus 1, and the data C is n plus 1 minus 2 times 1, so that's just n minus 1. And now I claim that if you take just a chain with n elements, you get the family of posets that you need. Let me just point out that the incidence algebra of this chain is just the quiver algebra of the equi-oriented type AN quiver. And this is it has been known to be fractional Calabi-Yau since the notion of fractional Calabi-Yau categories was invented in 1998. So this side is okay, and also it is the correct Calabi-Yau dimension. At least the one it matches the one of the conjecture of Chapoton. Now, what about singularities? There's such a thing that's called type A singularities, and up to a change of coordinates, you can write them as like this, and they have a category associated to them that is equivalent to the bound-derived category of AN. But the weight of this is not a trivial weight. This weight has the same data uppercase D and uppercase C. And so it gives the correct Calabi-Yau dimension. But I'm a little bit confused about what to do with a trivial weight. And I think someone should at some point explain this to me. I think there's something very simple that I'm not seeing. Okay, so this is a trivial, like we started off with a trivial weight and we ended up with a weight that was not trivial. But let's move on to Catalan numbers. What can we say about them? And so Catalan numbers, they count many different things. And among the things that they count are Tamari lattices, which will denote Tn, the nth Tamari lattice. And we mentioned before that the Catalan numbers, they satisfy a product formula. And here I recall that the sum of the numerator and denominator in the product formula should be 2n plus 2. If you compute the data of C for each n, you get n times n minus 1. And so in 2021, Baptiste Ronnerud showed that the bounded derived category of the Tamari lattice, of the nth Tamari lattice, is Calabi-Yau of dimension precisely n minus 1, n times n minus 1 over 2n plus 2, which fits also the Chapoton's conjecture. First thing, let me point out that Baptiste Ronnerud is my PhD advisor at philosophy. I finished my PhD already. And also, so he worked with Chapoton as a postdoc. And let me also point out this result that dates back to 2007 by Frédéric Chapoton, which says that on the Grothendieck group, it was already known that the star functor of the bounded derived category has order 2n plus 2. So Ronnerud's result is a sort of categorification of this older result by Frédéric Chapoton. But I want to point out also that it doesn't use this result in the sense that this result is based on some combinatorials, and the result of Ronnerud is based on other combinatorics. I will come back to this remark later. The limit of this example is that I don't know any singularities that fit this example so far, and I think Chapoton and Ronnerud, to the best of my knowledge, told me that they don't either. Okay, so out of the 3 examples that I mentioned in the first slide, I still have to talk about binomial coefficients, and so that was actually what I spent most of my thesis working on. So we'll now consider a family of lattices, mainly the lattices of order ideals of the product of 2 chains. Let me explain what these are. So you take a chain of size m and a chain of size n. You take the Cartesian product of them, so you get this little grid. And now you take the order ideals of this grid. So what is an order ideal? An order ideal is a subset of this grid that is down closed, so that if you have an element of the grid that belongs to your order ideal I, then all the elements of the grid that lie below that element should also be inside of your fixed order ideal. Also, let me make it clear that we compare elements in the grid term-wise. So these elements are couples. So we compare first entry with first entry, second entry with second entry. That gives the order relation on the grid. Okay, so this is the lattice that we call J and N. And so an order ideal can be described by these rims here, and like these paths in the grid. We draw a path and we say everything below, all the grid points below this path are inside of our ideal. And you can show that there is an isomorphism between the lattice of order ideals and non-decreasing sequences of length m with integer values in 0, n. And that is obtained by counting the number of elements of the grid that lie inside of your order ideal, just following these lines here. And so if we take the example of the path that was drawn here, if you count the number of elements of the order ideal that lie on this line, you get 2. Here you get 2 as well, 2, 2. Here you get 3, here you get 5, and here you get 5. You get an increasing sequence. Okay. The cardinal of this lattice is the binomial coefficient m choose n plus n, and we've already mentioned that it satisfies a product form. And so in 2019, Emina Yildirim showed that the Serre functor has finite order on the Grothendieck group of this of the boundary category of JMN. More specifically, that if you apply the Serre functor n plus 1 times, you get plus or minus the identity on the Grothendieck group. And she also gives a formula for this sign. And so we can already see that this n plus 1 does correspond to the sum of the numerator and denominator in each one of these fractions. And so one of my results from my PhD was to say that actually the bounded direct category of JMN is fractionally Calabi-Yau of dimension mn over n plus 1. This m times n is the data C that was predicted by Chapoton. It's something that you could already see through Yildirim's computation of this sign here. I mean, at least you could already conjecture it through this sign as well. Okay, and so again, we see this pattern of having like first a result of the Grothendieck group and then a result of the bounded direct category. And here, the result of the bounded direct category really relies on the result on the Grothendieck group, right? I really used Yildirim's combinatorics to do this. Her combinatorics consisted in identifying a family of really well-behaved representations or modules over the instance algebra of JMN and really computing their orbits under the Serre. And then what I did is like I managed to say, well, actually, sure, I mean this family of orbits already generated the Grothendieck group, but also they're enough to show that the entire boundary graph category is fractional Calabi-Yau. The other upshot of having this really nice family of representation was that I was also able to extract a tilting object and show that there is a derived equivalence between J and N and some very nicely behaved algebras called higher Auslander algebras of type A and N so on and so on. I will not describe them further, but they do generalize algebras of type A. So in that sense, it's I want you to think of them in that sense. Okay, but why does this matter, and why did I put this on the slide, on a slide with titled geometric aspect? That is because, oops, sorry. Hilario data showed in 2023 that there is an equivalence of categories between the derived category of these higher ascendant algebras of type A and a Fukaya-Seidel category, a derived category of a singularity SD. And so this starts to look like the geometric side of Chapoton's conjecture in the case of the binomial coefficients. But I still haven't had the opportunity to check that these singularities are quasi-homogeneous with the correct weights. They do have the correct Miller numbers, so it's really a good sign. But there's still some tweaks to check that it is it really fits the conjecture. So I will not discuss this derived equivalence any further, but I just wanted to point out that the work done to do the fractional Calabi-Yau property in this case really helped with this side of the conjecture as well. And I believe that it's not really coincidence, but it's not something that I've had really time to think about. So from now on, my goal is to talk to you about how to handle the fractional Calabi-Yau property for posets. And at some point, it will be clear that we have to actually think about lattices and posets. So I will start with some dictionary or the vocabulary that I like when talking about representation theory of posets, and then I will talk specifically about the fractional Calabi-Yau property. So the incidence algebras of posets and even of lattices and even of well-behaved lattices they are usually wild. We cannot have a satisfying description of all the modules. However, there are significant enough families of modules that we can actually describe, and I think one of them is anti-chain modules. So we start with an anti-chain, which is a subset of a poset made up of pairwise and comparable elements. Okay, now we need a little bit of notations. So you have your poset P, and for any element alpha of the poset, you'll denote by P alpha the projective and incomposable associated to that element, and S alpha the simple module associated to that element. In 2022, Iyamar and Marcinczyk showed that there's a one-to-one correspondence between anti-chains below an element. What I mean by below an element is that every element of the anti-chain is less than or equal to alpha. So one-to-one correspondence between these anti-chains, submodules of projective and decomposable associated to alpha, and modules with simple top S alpha. So more precisely, if you take an anti-chain, you can use it to generate a submodule of P alpha, and then when you can quotient P alpha by the submodule you generated, and you get the module with the top S alpha. And if you have the module with top S alpha, you can take its projective cover by P alpha. And then the kernel of that projective cover is a submodule of P alpha. And when you take a minimal family of generators for that submodule, you can extract an anti-chain. And so what I call an anti-chain module is this quotient M alpha C. Okay, and so using this, we can have a little, what I call a correspondence between modules over the incidence algebra of I'll put lattice here. Okay, never mind. Okay, so if we restrict to a lattice, we can have this little correspondence here by, and the way you go from right to left is by taking the support of the module, and the way you go from left to right is actually by identifying an anti-chain and then using the previous slide. So if you get so using the previous slide, we know that a submodule of a projective, it is generated by element of the anti-chain. So what is this? The support of this, that is an order ideal. And if you take a module with a simple head, well, that should be the complement of an order ideal within a certain sublattice. With complements of order ideal, that's order filters. And then you can ask yourself, what about module with simple top and simple sub? Because those, I mean, so the support of those are intervals. But then it also means that the elements of the anti-chain, they have a certain property, like it should be, if you restrict to the correct sublattice, it becomes a prime order filter. And this you can check on using only the anti-chain itself. Okay, so you can go from one to the other and turn like problems that are algebraic into problems about subsets of a lattice that have certain properties. Okay. And now comes a time where at some point we'll have to make it explicit that what we're using is a lattice. Because, so you replace now the poset P by a lattice L, and what you get is an anti-chain projective resolution that you wouldn't have otherwise. How do you get it? So you start with your anti-chain module M alpha. Here you have the projective presentation of M alpha, which is something you could have in any poset. So you start with the projective cover with the projective and decomposable P alpha, and then there is a surjection onto the kernel of this map of the direct sum of the projectives associated to the elements of the anti-chain. But then because you have a lattice, you can keep going by taking the meets of subsets of your anti-chain. And that really gives you the entire resolution. So each degree, you will take the meets of subsets of the anti-chain of a specific size. And you will do this until you just take the meet of the entire anti-chain. And so you get a resolution that whose length is exactly the size of the anti-chain C. But we have a little problem, and that is it's not this projective resolution is not always minimal. And so the second little dictionary correspondence will be about identifying root properties of these resolutions through root properties of the anti-chain. So I introduced two definitions. First of all, I will call a anti-chain inclusive if the order relation between the meets of subsets of the anti-chain behaves like the reverse inclusion. So meet of S less than meet of S prime if S prime included in S. And I will call it anti-chain intersective if the joins of the meets of subsets of C behave like the intersection of subsets. So what we're saying is that the lattice and poset operations on the meet sublattice generated by C should look like the power set of C in some sense. And so the one upshot of this of these definitions that, for instance, an anti-chain resolution is minimal if and only if the anti-chain is inclusive. Yes, and so that solves our first problem from before. And then the second statement here, it's just a fact because there's no if and only if statement. If you have an anti-chain that is intersective and you apply the Serre functor to your anti-chain module, you're actually quite lucky because what you get is still a module, but that is concentrated in the degree cardinal of C, which, if you remember, was the end of your anti-chain resolution. And so that's quite rare because in general, the Serre functor does not send modules to modules in the derived category. And why do I care about such statements? That is because what I want is to compute orbits under a circumference. And so if I can find modules, like a family of modules that it's stable under a circumference, or at least up to a shift, then that is way more manageable than starting up with modules and having to describe complexes that are whose homology is not concentrated in one degree. But yeah, so but here I do not, this is not a complete characterization of this property, and I don't have one. Okay. So here I drew some small lattices with examples of anti-chains. So here we have a Boolean lattice, and the anti-chain that I drew here is intersective. Here, this anti-chain is strong, but it fails to, sorry, it is inclusive, but it fails to be intersective because if you take the join of these two elements here, you don't get an element that can be written as the meet of elements of the lattice. You get this little black dot that is not related to them. And on the right is the diamond lattice, in which you have an example that really doesn't fit the vocabulary of the previous slide. Yes. Okay. And now I have some remarks. First of all, maybe you've noticed me slip up a bit. So intersective does imply inclusive for non-trivial anti-chains. Then, as I mentioned, with the properties that we had before, we can start identifying how to compute orbits under the circumference. So we should start with an anti-chain which is intersective. This way, when we compute its image, the image under the circumference of the anti-chain module, we still get a module, but shifted. And now, if it is an interval, we can keep going. What do we mean by that? Is that the module that we get, it is the homology in degree cardinal of C of a certain complex, and it automatically has a simple suckle. But what I know what to do is describe modules with a simple top. So I wanted to have a simple top so I can keep going, but then it has a simple top and a simple suckle, so it is interval. And so in that sense, really what we wanted to start off with is not just an intersective anti-chain, but also an intersective n-prime chain. Yes, and so we keep going. If we complete an orbit, we start another one. But then when do we stop? And to know when we can stop, we need to talk more about the fractional Calabi-Yau property for posets, and more specifically for lattices. So let me just recall the origins very quickly of the fractional Calabi-Yau property. It was introduced by Kontsevich in 1998. It generalized a concept that comes from geometry, but I am much more familiar with the following canonical example from representation theory, which is that the quiver algebras of type A, D, and E are fractionally Calabi-Yau. That is a result due to Miyashi and Nicotelli from 2001, and they showed this by computing derived Picard groups, which I find a bit intimidating, and I hope that what I present to you in this talk is less intimidating than that. Okay, so that was about the fractional Calabi-Yau property. And now I will introduce some results that we have that can help us reformulate the problem. So one of them is due to Hirsch and Iyama, and that dates to 2011. And it says that the following conditions are equivalent. So you could, if you manage to show that we have the fractional Calabi-Yau isomorphism on our finite dimensional algebra, which here is denoted lambda, then this is equivalent not to lambda being fractional Calabi-Yau, but twisted fractional Calabi-Yau. I will not define twisted, but I think the point here is that it's almost Calabi-Yau. But it's hard to get rid of this twist. And it's also hard to compute this isomorphism, but at least it's not as hard as computing an isomorphism of functors. So to show that two functors are isomorphic, you need to show that they match on objects and on morphisms. So this seems simpler, even though it can be complicated combinatorially. Okay, but then how can we manage these problems better? There's no answer in general, but if you restrict to some classes of algebras, you can hope for something that's more accessible. For instance, there's this theorem that Baptiste-Rognerud used to show that the bounded derived category of the Tomari lattice is Calabi-Yau. And the theorem says the following. So you fix a finite poset and you assume that this finite poset has your unique maximal or unique minimal element. And then you suppose that for each projective in the composable, you have the fractional Calabi-Yau isomorphism with fixed integers m and d. And then this is enough to get not only twisted Calabi-Yau, but actual fractional Calabi-Yau. So you restrict to a certain class, but then you get a result that it's a bit stronger. Let me point out that this assumption here about the projectives, it implies this isomorphism here for the incidence algebra, but it is a stronger assumption as well. Okay, so this is the type of result that I really like. But then there are other ways of attempting to study the fractional Calabi-Yau property by, really shifting the problem to something completely different. So if you like trivial extension algebras, you can go see this paper by Chan et al. From 2024, where they say that finite dimensional algebra is fractional Calabi-Yau only if it's trivial extension algebra. It's fractional Calabi-Yau. The point of this remark is just to say that you can reformulate this into other things as well. But it's just moving the problem and I believe that the complexity of the solution will always be somewhat similar. Okay, so how did I prove that the bounded derived category of JMN is fractional Calabi-Yau? This is with the following technical result. So instead of being in a finite poset with a unique maximal or unique minimal element, we will now fix a finite lattice and integers t and l. And we'll suppose that there exists a family of anti-chains indexed by the elements of the lattice, such that, so each element of the lattice has an anti-chain that lies below it. The associated anti-chain module is non-zero and satisfies the fractional Calabi-Yau isomorphism, and that each of these anti-chains, all of these anti-chains are inclusive. And in that case, you do get the bounded derived category is fractional Calabi-Yau. So we restricted to an even smaller class of finite dimensional algebras, but here what we gain is that instead of having to look only at the orbits of the projectives, we can look at any family that's big enough, that's made up of modules with simple top. So the projectives are part of this family, but also the injectives and the injectives don't work. The simple modules, but also you can look at intervals. And so you have more choice. If the orbits under the projectives are badly behaved, then you can look at other orbits. So you get a little bit more space to check things combinatorially. But that's for finite lattices. And so we can now update our little recipe from before. We start with an anti-chain which is intersective in prime, we compute its image on another time factor, and we get a shifted module. If the resulting module is an interval, we keep going. And if we complete an orbit, we start another one. And we keep going until each element alpha has a module with top S alpha, which lies in one of those orbits. Okay, but the question still remains, so how do you construct such an anti-chain in a systematic way? And I do not have an answer to this question. Okay, so the last part of my talk will be, I will be sharing my the screen of my tablet. So that will take me just a minute to set up. So maybe if you have questions, you can feel free to ask them now while I connect this. And okay. Okay, so you can see this new screen here, which is called What's Next, maybe plane partitions. Yes, okay. So plane partitions, let me write here, they generalize the poset J. So I call it J and N until now, but because here I use R, S, and T, I will call it JRS. So when I finished my PhD, I mean, ever since I finished my PhD, I've been thinking, oh, it would be very nice if I could just deal with this one generalization, like to just add one dimension and kind of convince myself and other people that the techniques are applicable in other contexts. And so I've been thinking about this with my with Karen Bauer, with whom I'm working now here in Bochum, and Emine Rildirim, who did the combinatorial model for JRS. So let me define plane partition. And so these are order ideals again, but this time in the product of 3 total orders. So of size R, S, and T. Here I have a little drawing in a 4 times 5 times 3 box, and this little configuration of cubes inside the box, that is an order ideal. And so it is stacked towards this vertex here, which is the minimum of the grid in the way that I decided to draw it. If we look at it from above here and count the number of boxes in each column, we can write these in a little this little table here, and that gives us a table with increasing columns and rows in these directions, which is the notation that we will use from now on. And this, something like this lattice, the set of all ideals of this box, they've been studied for a while now. So we have they were counted in 1916 by Macmahon. And we have this formula here, which is maybe significantly more complicated than the formulas that I gave in one of the first slides of this talk. But so they generalize R choose RS, that's 1, and 2, they have a product formula. And yes, maybe that's an exercise, and if you want the trick on how to do this, you can go look in Chapoton's paper, it doesn't treat exactly this formula, but there's one that's very similar to it for alternating sign matrices. And the idea is the same for this one. And the Calabi-Yau dimension that you get from this product formula should be this one, RS T over R plus S plus T. And so when you take T equals 1, you do get the R over S, sorry, R times S over S. We have for JMN, JRS. Okay, so this is really a generalization of the JRS case. So how can we try and compute this in here? So we will now focus on a smaller example, just more so that we can see what's going on. So we will look at a 3 times 3 times 5 box. So 3 times 3, and here the maximum value is. And so the Calabi-Yau dimension that we would like to obtain is 3 times 3 times 5, that is 45. Yes. Over 3 plus 3 plus 5, and that is 11. Okay. Let me see. I still have some few minutes. And so we start off with a little partition here. And I picked one where the regions are all squares. Like here, we have regions with a certain value that have like funky shapes. And so I didn't want to have that here, except for these little rectangle here. And then also in most cases, the difference between consecutive entries is just 1. The only places where it's not is here. This makes it more manageable. At least when we're trying to get an idea of what's going on. And let me point out that, yeah, so this is something that Yildirim told me, like she knew what would happen. So she knows what happens in a case that is just on one line. At least like she worked on it quite a lot. And so she had all these little tips on how to try and generalize. Okay, so we have a plane partition. Now we need an anti-chain. And so the anti-chains will be indicated with little boxes. And what the boxes say is when they're blue is just to remove one from this box and keep the rest the same. So, and that gives you an element that is below this plane partition. So the element of the anti-chain associated to this blue box here will have the same values here and just a 1 here instead of the 2. And you do the same for each of the other boxes, except for the red box here where you remove -2 as indicated next to it. Okay, so this is an anti-chain. And then how do you get, then this anti-chain will have the property primeness that makes it define an interval. So it remains to find the lower bound of the interval. And how do you do this? Each element of the anti-chain gives you a constraint that is satisfied by all the elements of the interval. And so the lower bound of the interval is the unique partition which satisfies, which is minimal while still satisfying all these constraints. So the constraints, they're all on these numbers, and so we minimize everything else, and that means putting these 2 zeros over here. Okay, so that is our interval. And so now can we compute the is also intersective. And so what does it mean to compute the Serre functor? Well, as you recall, if it is intersective, it means that we need to understand, we apply the Serre functor, we get a complex, and we need to understand the homology of this complex in degree size of C, cardinal of C. And so this means that we first need to compute the meat. The meat of the elements of the anti-chain. So we need to apply these transformations, this transformation indicated by the boxes, all at once. So, and what we get, is this new partition. And here we also, it comes with constraints, and when you maximize everything given those constraints, you get the upper bound of the interval. And then you can reverse engineer the anti-chain here. And it is again an intersective anti-chain, so we can keep going. And in that case, it kept going, and I was very happy. At the end, you get exactly 11 anti-chains, modules before you come back to the one you started with. So we get the correct size for the orbit. And what are the shifts? The shifts are always the sizes of the anti-chains. So the size are like we just have to count the boxes in each case. And I counted the boxes and I found 45, and I was very happy. And so I did this to a bunch of other anti-chains. And it all looks really well behaved. There's only one problem. I don't understand the red boxes. It's very frustrating. I really thought, Yildirim and I really thought that it would be a straightforward generalization. It's probably accessible, but there's these little red boxes here and here, and they don't behave exactly the same, and we don't know when to make which choice in order to know exactly what family of anti-chain modules we need that are stable under their star functor, that is big enough in order to have the fractional Calabi-Yau property for this family of lattices. And here are, if you like this little recipe I gave, you can I can guarantee you that these little these anti-chains, they work. I mean, they have nice orbits. And I will stop here. Thank you for your attention.
Thank you very much. Dominic is there. Okay.
Yeah, sorry, I was lost for a few minutes because of the connection. Thank you very much, Tal. So, do you have some remarks or questions? No.
Hello.
I would have. Okay. Sorry, Gunnar, please. Yes.
Yeah. So when power of the self-functor is a shift, is there any, say, are there large classes of posets for which this is known, or is there a general theory for I guess
so far no.
So far not. Okay.
Yeah, not that I know of. Yes, it's
no. Are there any simple obstructions, so you can tell if the poset has this property, it cannot happen, or?
Okay. There's a paper by. I need to. Let me see if I have it here. There is, okay, I cannot, oh, I'm really sorry. This is the name of the people that wrote the paper really elevates my memory. If you give me, can I have a minute? I will try and find this reference in there are, I think there's something that could answer your two questions. So here. And okay, it's if you go, there's a paper by Diveris, Purin, and Webb from 2017, or actually they have something a bit like a construction that's a bit more general. And they also have, and they use this construction to figure out posets that don't have the fractional Calabi-Yau property. But I haven't been using their techniques. It doesn't work. I mean, it's not complete. I think it's not a complete classification. And in general, it's kind of hard to show and things like that.
So the authors were Wen and
Yes.
once more, please. Could you repeat?
Purin and
Okay.
in 2017.
Oh, sorry.
Yeah.
Okay. Thank you. Yeah.
Okay. So concerning number sequences, so you mentioned the Catalan numbers, Tamari lattices, and then the order ideals in the products of two total orders, which you did, I believe, JMN, and then you come up with Chapoton, who did essentially order ideals in the product of three plain posets, or order ideals in a product of three linear orders. And it seems, of course, very natural to guess that this would generalize to any product of total orders. But what you I guess Chapoton's recent result was very recent in 23, so it's probably if he did not do it for 4 or 5 or 6 orders, it's probably a tough thing to extend it to his product of.
Yeah, so it's a conjecture by Chapoton. It's not known yet. This for the plane partitions. I don't know the formula in general, unless I missed something. But I think I talked to him recently. I think it's still a conjecture. And so for products of more chains, I don't know what I don't know formula that counted. I don't know if it has a product formula. Maybe it does. I want to point out that they do, like, the complexity increases by a lot by adding one dimension.
So that they have a product formula, is that yeah, but is that essential for okay, so but that's not essential for say a fractional Calabi-Yau property, or
in itself, no, but it's a part of the story by Chapoton. Yeah, it's in itself, no. There's no reason that all posets that are fractional Calabi-Yau should come in these families. I don't think that is. I don't think that would be true. But specifically, I find it very interesting to look at these. I mean, I think this conjecture is very fun to look at when specifically they come in these families.
okay, thank you.
Thank you very much.
Okay, are there other questions or comments? No.
I have a couple of questions. They're not really questions, but so the first is just at the beginning you had these product sequences, like, and they're not necessarily unique. Do you have any, like, can you say something about like when are sequences like equivalent?
No, that's a good question.
Or do you know
I
any
don't have an answer for this. I think
Okay.
it's a good question, and that someone who's interested in these conjectures should think of it. It can be me, it can be someone else. but it's a good question. I don't have. I've been making small computations, but I don't have any.
I see. The second
answers.
question I had was, maybe this is like a reflection of my confusion, but so there are some places where you mentioned, okay, you used to insert certain technical results using that involves some functorial properties. But I was wondering, like, how do you figure out what sort of examples to look at? So you had these things involving Tamari lattices and so on, but I was wondering if like there's like a subfamily where you can say, okay, well, these sorts of properties are things we look for in like in fractional Calabi-Yau things. And like, or any like necessary conditions for posets other than like these anti-chains. Or not, of course, in general, this might not be feasible, but I was wondering like, how do you look for like the right sort of examples to look at? Maybe that's sort of the main question.
I think I don't know. I think so. One thing is, so you can this JMN family. I think it's a very good starting point to think about these things.
Yes, I like these examples.
Because so you can write any poset as any finite poset as a subposet of a product of chains. So you can always, so there's in the minimal number of chains needed, that's the poset dimension.
Right.
So you can always write posets as sequences. But of course, not necessarily non-decreasing or increasing sequences. This is a rare thing. But you'd say, okay, let's look at sequences that are easy, non-decreasing, and then maybe we can try and think, well, if I have other types of sequences with other other properties, maybe we can move stuff about JMN to more general case. So I haven't been able to do that, but this is why I think JMN is a good starting point and why I like this example so much. Yeah, that's maybe one way of answering. I don't have a better answer for where to start.
It's okay. Also, I think I get some idea of like what you're thinking about. So, okay, thanks.
Dominique.
Sorry. Okay, sorry. Other questions or remarks? Okay, if not, we thank Tal again for her very nice talk. And we'll have Ulf Kuhn about utilizations of post-Lie algebras in number theory and in particular multiple zeta values and polylogarithms. Okay, thank you very much to you all. Bye.
Thank you.
See you.
Bye. See you.